Hello everyone, on this part we have scatter diagrams and correlation. We had this part before, recall. So the response variable is a variable whose value can be explained by the value of explanatory variable. So that is this one. This is like having output and here on this part this explanatory variable is input. And usually for this case, for input we're gonna use x and here is y. So based on that, using explanatory variable, we conclude response. In other words, when our domain is x, so our domain is explanatory variable, using that one, our response is y. So that x is explanatory and here this is response. Okay, now try and interpret scatter diagrams. Here, scatter diagrams is a graph that shows on this part we have a relationship between two quantitative variables. And also, you should use point for each individual. So each individual in the data set is represented by a point. So point for each one. And then for explanatory variable, we have that one on x-axis and response variable is on y-axis. So this explanatory is on horizontal axis, which is x. And here response variable is on vertical axis. So we're going to use y for that one. Okay, now example. Here we have this table and we have two columns. The first column is showing with x and here is y. Okay, so the data shown to the right are based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill distance of 5 feet rock increases with the depth at which the drilling begins. So depth at which drilling begins is the explanatory variable. So this one is explanatory variable. And time to drill 5 feet is response. So this is response. Draw a scatter diagram of the data. So based on these, we're gonna draw this scatter diagram. So what we have here on horizontal line, here is x. And here on y-axis, we have time. Now, okay, let's see what points we have. Here on x, we have the lowest one is 35, and that is up to 190. So I'm using So that is 50, 100, 150, 200. On this side, for y-axis, the lowest one I have is 5.88. So these are in order. No, these are not. Okay. So these are not in order, but that one is the lowest one, the lowest point we have. And the highest one is 7.9. Okay. So I'm going to use these on y-axis. Now finding all these points. So here on x we have 35 and y is 5.88. That's like that. Then 50, 5.99. It's very close to 6. Then after that, 75, 6.74. 95, 6.1. 120, 7.47. 103, 6.93. Okay, change this one a little bit on the side. Okay, then after that we have 145, 6.42. 155, 7.97. 160, 7.92. 175, 7.62. And 185, 6.89. And 190, 7.9. So these are our points and this scatter diagram. Next page. Now in this part, we have scatter diagrams that show the type of relation that we have between two variables, so type of relation between x and y. And the first one that we have, this called explanatory, and so here x-axis here is explanatory and y-axis is a response. So for all of these we have explanatory and response for x, y. Now the first one, this is linear because we have all these on one straight line, are very close point, and these points are very close, so we can draw a straight line here. like that. And same thing for this one. But here I'm not able to draw a straight line. Here same thing, not able to draw a straight line. And also for this one, we don't have any relation between x and y. But here, as you can see, we're not able to draw a straight line. That's why this is non-linear. And here also is non-linear. And but these two are linear. But the difference between these two is that here slope is positive and here slope is negative. So for this part, slope is positive. So we have positive slope, and here we have negative slope. Okay, so this part is for positive and negative. Two variables that are linearly related are positively associated. So that one is this part. When the value of one variable increases, the value of the other variable also increases. So if x increase that way, or y also will increase. But in this case, we have different case. Two variables that are linearly related are negatively associated if whenever the value of one increases, the value of the other one decreases. That's why we have negative slope. So here is positive slope, but this one is negative. Now next part, we have linear correlation coefficient or Pearson product moment correlation coefficient. So we're gonna use correlation coefficient for this one. What we have here is sample. So sample correlation coefficient, showing with R. Here, these x's are data value, and also for the upper y is value. So these two are data value. And also this n is sample size. So n is sample size, and n minus 1, this is degree of freedom. And also, so I have all these here. So we have x bar is sample mean. We already know about that one. So it's a sample mean of the explanatory variable. And here this S is sample standard deviation. We had this part before. So it's sample standard deviation. When it's S is sample, when it's sigma is for population. Y bar is sample mean of the response variable. So since we use x for explanatory and y for response, it's same thing for sample. So x bar is sample mean and y bar is sample mean for explanatory variable, and this y bar is sample mean for response variable. And same thing for sample standard deviation. So this sx is for explanatory and this sy is for response. And we already know that the n is sample size or number of individuals in the sample. Okay, next page. we have property of the linear correlation coefficient R. Number one, the linear correlation coefficient is always between -1 and 1. So we always have this for. If our correlation coefficient was equal to 1, then a perfect straight line, we're going to have a perfect straight line, positive linear relation exists between two variables. So what that is, this means we have 100% positive association. Number 3, if R was equal to -1, so that is positive. Here is negative. Again, exactly 100%. But since we have negative, now we have negative association. Okay, so the closer R is to +1, the stronger the is the evenness of positive association. So what that is, if R is then the closer is to +1, that means that the closer is to have 100%. For example, if you have 90%, and so this is what that means. You may have 90% like that. And then number 5, the closer R is to -1 with negative slope is the evidence of negative association. If R is close to 0, then little or no evidence exists. If R is close to 0, there is no evidence. What that means, no linear relation. And also number 7, the correlation coefficient is not resistant. Therefore, an observation that doesn't follow the overall pattern of the data could affect the value of the linear linear correlation coefficient. So this is what that means when it's non-resistant. Okay, let's see what we have here. So here we have all these that we had on top. Now starting from left, here we have R equal to 1. So it's +1. And that's how we have perfect, so what is that? Okay, we have perfect positive correlation. Exactly here on top we have that one, perfect positive. We can have a straight line here, but slope is positive. This is 100% positive association. And here on right we have a -1, so this is 100% negative association. Guys, we are able to draw here. I'm able to draw a straight line and having all points here on one line. Same thing for this part. Here also I'm able to draw a straight line, but I'm not able to have all points on that line, but these points are very close to this line that I have here. So that is high negative correlation. It's negative again because we have slope is negative. Same thing on this part. By drawing a straight line, we can have some of the points on that line, but we have some outside this is straight line, but these points are very close. So this is high positive correlation because we have positive slope. And what is this one here again? Straight line like that, because I can have some points on that one, but we have okay, these are not that close, these points that we had here on the previous part. Same thing on this part. See, I can have some of these points on that straight line, but not all of them. But obviously these points are they have negative association. Now this one, what we have here, if I try to draw like that, this is totally wrong. What if I wanted to draw this way? See? So that's why we're not able to decide what that means. There is no relation, no correlation between these. I'm not able to draw a straight line. So this is wrong. So no correlation for that part. Now correlation, when the two sets of data are strongly linked together, we say they have a high correlation. So we cover that point. The word correlation is made of co, meaning together. So what the co means together, and the relation. Okay, now here we have example. Match the linear correlation coefficient to these scalar diagrams. The scales on the x and y axis are the same for each diagram. Okay, so if I try to draw this a straight line, okay, I'm gonna draw that again. Okay, and here also, let's try it. For this part also I can draw a straight line. And same thing here. This is a straight line. Okay, now let's see what we have. So, the highest positive correlation, which one is? Here on the first one, these points are very close. So the highest one belongs to this part. I'm going to choose this part D for this part. So R is 0.946. And then after that, which one is the highest between these three? Highest correlation. Obviously for all of these we have positive, so highest positive correlation is this one. These points are closer than what we have here because this is too far from this straight line, or from these points that we have on the other side of this straight line. So after that we have this one, and that is part A. So R is 0.787. And then after that, between this one and that one, I have more points here on top that are not on this straight line. But this one I have less points, so I'm choosing to have this 0.523. So between these two, the highest one is what I have here. And finally, this has the lowest positive correlation. Now, example number 3. Determine the linear correlation coefficient of data-reading data using the formula given. So these points are exactly what we had on the first page. Here on this table, on the first part, are same x and y. Okay, so depth is x and time is y. So that is, this one is explanatory variable, and here is response variable. And what are these data? These data are, so we're gonna use that one, but we already have these data for each part. So this is x I minus x bar divided by sample standard deviation for explanatory variable. And here is yi minus y bar divided by s for sample standard deviation for response variable. And what is this one is what we have on top. So this is multiplication of these two, multiplying these two. And this is x bar, and here is y bar. So we have sample mean, sample standard deviation, and here also sample mean and sample standard deviation for x and y. And what this number is, this is sum of all these points. So adding all these points is that one. So that is addition of these two. Okay, multiplying these two and then adding all these data. Okay, so we were asked to find, use this formula to find correlation coefficient. So R is equal to, we already have all these data. So on top we have 8.50, 10, 37. Divided by n minus 1. How many numbers we have here? We have 12. So n is 12. We have 12 minus 1. Divided by 11. Rounding it, it's 0.773. Since this one is positive, what that means, we have positive association. So using that correlation, we have positive association. Okay, we finish this one. So our correlation coefficient is approximately equal to 0.773, and that is positive. Now on this one, we should find if a linear relation exists between two variables. Testing for the linear relation. Step 1, determine the absolute value of the correlation coefficient. Step 2, find the critical value in this table here. That is from our textbook. And step 3, if the absolute value of the correlation coefficient is greater than, the point is here. So if the absolute value of correlation coefficient is greater than the critical value that we have here from here on this table, we say a linear relation exists between two variables. Otherwise, no linear relation exists. This one is important. So if it's greater than, then we have linear relation. If not, no linear relation. Let's have an example for that point. Example number 4, using example number 3. So we're going to use this example number 3 and using that or. Determine whether a linear relation exists between time to drill, feet, and depth at which drilling begins. So comment on the type of relation that appears to exist between time to drill, 5 feet, and depth at which drilling begins. Okay, so we already know that sample size from previous example was equal to 12. Okay, now based on step 1, determine the absolute value of correlation coefficient. We have that one is 0.773. So the absolute value of positive number, we have positive number. The absolute value of negative number, it's again positive number. So absolute value of that one is 0.773. Then step 2, find the critical value in table. Here our n is equal to 12. So that one. Based on that, our critical value is 0.576. Okay, so we have this number is 0.576 because our sample size is equal to 12. So critical value is 0.576, and this was from table on previous page, because this is page number 4. And from example 3, we had this part. Our correlation coefficient was equal to 0.773. So step 1, you should find absolute value of R, which is equal to positive. So this was a step 1. This one was step 2. And step 3, we should compare this with critical value. Is this one? We should add, is this one greater than critical value? So here this part is step 3. So this number is greater than critical value. What that means, there is a positive linear relation. See here. If absolute value of correlation coefficient is greater than the critical value, we say linear relation exists. And here we have greater than. Okay, now example number 5. The following data represent the number of licensed drivers in various age groups and the number of fatal accidents within the age group by gender. So these two columns this part is for males and this column and this column is for females. What we have here, so this is X, here is Y. Here again we have X and Y. So this is explanatory variable for males and response variable for males. And this part X and Y belongs to that group for female. Part A, on the same graph, draw a scatter diagram for both males. I already have this part here. Be sure to use a different plotting symbol. So here I used, for males, I use this square and positive sign for females. So to be able to graph that one, first step is that okay, we're gonna use the TI-84. First press second. After second, press 0. So second, 0, then scroll down to find diagnostic on. So here is what we have. So after pressing second, then 0. So we have 0, 1, 2, 3. Pressing 0. On top of that, you can see catalog. So here is catalog. And after that, scroll down to find diagnostic. You should have this step to be able to graph. Because if you don't, you may have error. Scrolling down to find diagnostic. Okay, so here is diagnostic off. Here is diagnostic on. You should choose that one and then enter, again enter. So you should see done. That. And then now after that, we're able to enter our data. So press that. Choosing the first one, edit, enter. Then after that, enter all the data that we have in that table. The first two columns, these two are for males and the third and fourth is for females. After we entered all these data, now, okay, here is asking to graph it first. Okay, let's graph it first. So first, press second. Then after that, on top of second, you have y equal to. So second, then press that bottom, you have y equal to. On top of that, you can see stat plot showing with F1. So stat plot F1. Press that one. You'll see the sport. Okay. Now choosing, we have two plots here. So one for L1, L2. The other one I'm going to choose for L3, L4. So enter here. After that one, choose number 1, enter. We have this page. If you had this one on, this one was off, you should move that one to on. Type of diagram we have scatter, so the first one is, and the point is that for X you should have L1 and for Y L2. If you have different thing, you should type that in. For example, on your calculator, so here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 is catalog, 1 is L1, 2 is L2, 3 is L3. So I'm reading what I have on top of each one is showing with blue color. So you can change these by pressing 1 for L1, 2 for L2. We already have L1, L2. Now for males, I'm choosing this port square and choosing this color blue. Okay. And okay, going back by pressing second, again, second y equal to. So again, I have this page. Now I'm choosing number 2. I'll scroll down to choose number 2, enter. So same process. I should have that on. So choosing that one. And then here for X, now I have L3, and for Y I have L4. You may have L1, L2, so change these two. And also I'm choosing this positive sign for female group and color red. Next step, now you should choose window. It's on the first row of your TI-84 calculator. So on top you have window. So what you have on top is Y equal to window, zoom, trace, and graph. We're gonna use window and then later graph it. So we have window. Here, what you need to choose is that you should know based on the points that we have for X, the points you have for Y, what is the minimum and maximum value that you have for each group. For example, for the smallest value that we have for X on the first column, we have 12. I want to choose smaller than that because I want to have a interval. So interval is 5 and to 20,700. So we're gonna have all the points that we have in the first column X. Those points are in this interval. So we're choosing this mean and max based on the point that we have in each column. Same thing for Y. Y we have 227 as the lowest one, as the smallest number that we have. So I'm choosing to have 200. You can choose 220, but it's better to choose this one because I want to have all the points in that interval when we graphing it. And Y maximum value here is 8,595, so I'm choosing to have 8,800. Okay, so now graphing. Again on top, on first row of your graph, on the right side you have graph. So press that one. Okay, so here is our scatter diagram. These blue are for male and these are for female. Okay, so we graphed it. So I have that graph here. Now part B, based on these scatter diagrams, do you think that insurance companies are justified in charging different insurance rates for males and females? Why? Okay, the answer is yes. Because from scatter diagram, males tend to have higher fatal crash rate. So see, I have these points are on top, but these points are here under this straight line. And also we have higher correlation coefficient, or in other words, for example, or here we can say this is 0.870 something, and here is 0.500 something. We're gonna calculate that, but for now, just based on what the graph is, the answer is yes. So from scatter, so males have higher crash rate. Part C, compute the linear correlation coefficient between number of licensed drivers and number of fatal crashes for males. Okay, now we should calculate R. So press that, edit. So we have all these data. And then press stat. Calculate. Now choosing number 4, enter. So here we have L1, L2 based on the first and second column. Enter, enter, again enter. So here is what we have is this RA's correlation coefficient is 0.883. So I'm running that to have 0.883. And then part D is compute the linear correlation coefficient between number of licensed drivers and number of fatal crashes for females. So let's find that for females too. So again, stat. Okay, now choosing number 4. So both of these, for both of these, I'm choosing this one. Enter. Now here again we have L1, L2, but our data are in the third and fourth column. We should have L3, L4. So changing that by pressing second, number 3. And for Y we have second, number 4. I have these two instead. Then after that, enter, enter, enter. I think we have 3 or 4 times. You should press enter. Now R is 0.836, so I'm rounding to 3 decimal place. The answer for part C was running was 0.883. And for part D was 0.836. Part E, which gender has a stronger linear relation between number of licensed drivers and number of fatal crashes? Why? So obviously males, because this one is higher than what we have here for females. So the answer is males. Harry, slightly stronger. Linear relation. That is 0.883 versus 0.836. So this was for males, and here was for females. Okay, we finished the sport.